My name is Riksit. I am from Triple E branch. Today I am going to explain about irreducible M matrix. Introduction and preliminaries. What we deal with n into n real non-negative matrix and n into n real negative matrix. Either matrix whose off-diagonal elements are non-positive or a non-negative matrix B. Let PB denote the spectral radius of B and PKB denote the maximum of the spectral radius of all k into k principal submatrix of B. Particular interest in the class of Z matrix or the M matrix. Either those matrices A is equals to Z whose from is A is equals to Ti minus B, where B is greater than or equal to 0 and T is greater than PB, and the non N naught matrix. Either those matrix A is equals to Z whose form is A is equals to Ti minus B, where B is greater than or equal to 0 and Pn minus 1, B less than or equal to T less than Pb. Following Seidler and Peter, we let we let K denote the class of a matrix and K naught the closure of K. E equal to K naught means A equal to Ti minus B, where B greater than or equal to 0 and T less than or equal to 0, greater than or equal to Pb, T greater than or equal to Pb. Pan examinated those matrices in Z whose determinant is negative, whose principal minor of Z over n minus 1 are negative, and whose principal minor of n minus 2 or less are positive for n greater than or equal to 2. Turning this well for n greater than or equal to the job, examine those matrices A such that A is equals to 2 and 2 on principal submatrices of order n minus 2 or less are in K naught and 3. At least one principal submatrix of order n minus 1 is in N naught. We shall call such a matrix an F naught matrix in honor of Fan. A matrix A is irreducible if there is no presumptions matrix P such that PAP P power T is equal to A11, A12, A0, A22, where A11 and A22 are square. If A11 is a non-singular principal submatrix of n into n matrix, the sure complement of A11 is A2 denoted by A by A11 is defined as follows. Let P be a permutation matrix such that PAP P40 equal to A11, A12, A21, A22, where the rows and columns of A11 and 22 are in the same increasing order as in A. Then the surf complement of A11 and A is A by A11 is equals to A22 minus A21, A11 or minus 1 A12. In section 2, a criterion of irreducibility is obtained in terms of the irreducibility of the surf complex for a certain class of Z matrix, which includes the M matrix, the N naught matrix, and there is F naught matrix. Feiler and Peacock showed that M matrix has an positive eigenvalue M of A of minimum modulus. Similarly, in the author showed that an N naught matrix A has a negative eigenvalue N of A of minimum modulus, and that of F naught matrix has exactly one negative eigenvalue. In L.J. Watford Jr. showed that if A is an M matrix and A11 is the principal submatrix of A, then M of A less than or equal to M of A by A11. Further, we showed that if A1, A2 and so on, A n minus 1 is a sequence of principal submatrix of M matrix and A, and for each I, 1 is less than or equal to I is less than or equal to n minus 1. A1 is an I into I principal submatrix of A of I plus 1. then m of a is less than or equal to m of a by a1 less than or equal to m of a by a2 less than or equal to so on m of a by n minus 1 is equals to a by n minus 1 a n minus I. In section 2, using the irreducibility criterion, these inequalities are shown to be strict when A is irreducible. For an N0 matrix for an non-singular F0 matrix, similar inequalities are obtained for a negative eigenvalue. 1 is less than or equal to I is less than or equal to n minus 1. A1 is an I into I is matrix of where I plus 1. Then m of A is less than or equal to m of A by A1 less than or equal to m of A by 2 less than or equal to so on m by m of A by A n minus I is equal to A by A n minus 1. In section 2, using this irreducibility criterion, these inequalities are shown to be strict when A is irreducible. For an n-not matrix, for a non-singular reflex matrix, similar inequalities are obtained for the negative eigenvalue. In the spectrum of 3 into 3 circular M matrix is characterized. In section 3, we characterize the spectrum of 3 into 3 circular n-not matrix. In Markov defined an almost principal minor of a matrix of as follows. If alpha and beta are strictly increasing sequence of n is equals to 1, 2, and so on n of the same length, then a of alpha by beta is the minor of A with rows indexed by alpha and columns indexed by beta. We say that A of alpha and beta is an almost principal minor of an A. If in the sequence of alpha minus beta, mod of alpha minus beta is equals to mod of alpha 1 minus beta 1, comma, mod of alpha 2 minus beta 2, comma, and so on, mod of alpha k minus beta k. Exactly one term is non-zero. Markov then showed the matrix whose inverse or M matrix has non-zero negative almost principal minors. Along these lines, John showed that matrices whose inverse or N0 matrix has non-positive almost principal minors. In section 4, we show that matrices whose inverse are F0 matrices have non-positive almost principal minors.
Show complements of Z matrix, M matrix, and minus matrices. We first prove the following irreducibility criterion: the case where the order of 0 A11 of A11 is equal to 1 done by Johnson. For the Varga and Chi corollary to Lemon showed that if A equal to K naught, it admits an LU factorization into K naught matrices non-singular L, and if A is irreducible, then A of K, the active arrays K after K steps of the Gaussian elimination process. The irreducible, then they note that if A equal to K naught is irreducible, or if A equal to K, then A admits an LU factorization into K naught matrices with non-singular L. It is well known that if A11 is the non-singular K into K principal submatrix of A in the upper left corner, then A bar K is equals to A by A11 and 2. Second, if A equal to K naught is an irreducible, then A11 equal to K. Correcting these facts, we see that the Varga and Chi has shown if A equals to k naught is irreducible, then A par k is equals to A by 11 is irreducible. We show in lemma 2.1, 2.12 below using an inductive proof that this holds for all A equal to Z such that A11 equal to K. Lemma 2.1. Let M be the matrix prioritized as M is equals to A11, A12, A21, A22, where A11 is non-singular, A12 is not equal to 0 and A21 is not equal to 0. Then if M by A11 is irreducible, then M is irreducible. If M is equals to Z is irreducible and A11 is equals to K, then M by A11 is irreducible. Proof. First one. Suppose that M by A11 is irreducible and then P is permission of matrix such that PMP over T is equals to AB0D. If A11 is a proper principal submatrix of A, then there is a permutation matrix Q such that QPMP power T Q power T is equals to rho A11 A12 B1, rho 2 A21 A22 B2, rho 3 0 0 D. Thus M by 11 is reducible, which is consideration. Similarly, M by 11 is reducible if A11 is proper principal submatrix of D. So assume that A11 is non-proper principal submatrix of A or D. Then there is a permutation matrix R such that RPMP power T R power T rho 1 M11 M12 M13 M14 rho 2 M21 M22 M23 M24 rho 3 0 0 M33 M34 rho 4 0 0 M43 M44, where A11 is equals to rho 1 M22 M23 rho 2 0 M33. Again we have the contradiction that M by M11 A11 is reducible. 2. Suppose that M is equals to Z is irreducible and A11 is equals to K. Proceeding inductively on not of A11, the theorem is true for not of A11 is equals to 1 by Johnson result. So assume that not of 0 of A11 is equals to K, where 2 is less than or equal to K is less than or equal to n minus 1, and that the theorem is true for all principal submatrix of M of order less than K. We may assume that the A11 has the form A11 is equals to rho 1 A11B, rho 2 CD. The permutation matrix P is such that PM P power T, rho 1 D, rho 2 F and G. Now D is equals to K, and thus M by D is equals to G minus FD power minus 1 E is equals to Z is reducible by the indication hypothesis. Hence, since M by A11 is equals to M power M by D by A11 by D by the arbitrary arbitrary Heisenberg quotation formula, the result flows Johnson results. Directly from the theorem, we have the following corollary. Corollary 2.2. Suppose M is equals to K naught and M is patronized as in 2.1 where A11 is equals to K, or comma A12 is equals to not equal to 0 and A21 not equal to 0, then M is irreducible if and only if M by A11 is irreducible. It is also the interest that the generalization of Varga and Kai's lemma to M not equal to K naught also hold by complete analog argument. That is, we have to following theorem. Theorem 2.3, let A is equals to Aj is equals to rho 1 11 A12 rho 2 A21 A22 be an n into n Z matrix such that A11 is equals to K is a K into K principal submatrix. If there is a path from vertex V to vertex Vs in the directed graph Gn of A of Gn of A for such r is not equal to s and mine rs r comma s greater than k. Then there is an associated path from the vertex vr to the vertex vs. In the directed graph g n minus k, a bar of k, g n minus k of a bar of k of the matrix, a bar of k is rising in the k step of the Gaussian elimination applied to A, where the vertex of Ga n minus k of A bar of k are defined to be the V of k plus V of k plus 2 and so on Vn. Johnson noted that a naught matrix A has exactly one negative eigenvalue which we will donate by n of A, and if A11 is non-singular principal submatrix of A, then A by A11 is also an n-naught matrix. We wish to examine the relationship between n of A and n of A by 11. Theorem 2.4. Suppose that the n-naught matrix A has the form A is equals to row 1 A11b, row 2 C and D, where A11 is equals to K, then n of A by A11 is less than of n of A. Proof. As you can see the formula at 2.2, we need to solve this. Now a now a power a power minus 1 is irreducible, since a by a11 minus 1 is a proper principal submatrix of irreducible non-negative matrix of a minus 1, and since delta mod of delta greater than or equal to n of A for all delta is equals to SPA, where A is an n-naught matrix, we have, as you can see in the formula, and the result follows. The proof of the next two results are quite similar to the proofs of the Watford's result for M matrix, but are included for completeness. Theorem 2.5. Let A be a non-zero matrix where A is equals to row 1, A11, A12, A13, row 2, A21, A22, A23, row 3, A31, A32, A33, and B is equals to row 1, A11 is equals to A11, row 2 is equals to A21, A22. With B is equals to K, then n of A by B is less than n of A by A11 less than n of A. Proof by Carpentry-Heisenberg-Courant formula. A by B is equals to A by A11 or by B by A11. By applying theorem 2.4 twice, we obtain n of A by B is equals to n of A by A11 by B by A11 less than n of A by A11 less than n of A. Theorem 2.6. Let A1 A2 so on A K AK be a sequence of principal submatrix of an n-naught matrix A, where AK is equal to K is a K into K principal submatrix of A, and for each I 1 less than or equal to I less than or equal to K minus 1. AI is an I into I principal submatrix of A I plus 1. Then the formula. Proof. This follows the successive application of theorem 2.5. In a similar manner, we show that the Watford's inequalities are strict for the irreducible M matrix. To establish this, let A be a reducible M matrix. Let AI be an I into I principal submatrix of A I plus 1 for 1 less than or equal to I less than or equal to n minus 1 for each I. 1 is less than or equal to I less than or equal to n minus 1 A by A power minus 1 is a proper principal submatrix of the irreducible non-negative matrix A minus 1. And by argument similar to the proof of theorem 2.4, we have the formula M of A less than M of A by AI. Now suppose that I less than j less than n, then AI is a proper principal submatrix of both A and AJ, and by corollary 2.2 A by AI is irreducible M matrix by applying the arbitrary Heisenberg quotation formula, and 2.3 twice we obtain M of A less than M of A by AI less than M of A by AJ. By successive application of 2.4, it follows that M of A less than M of A by AI A1 less than M of A by A2, and so on. M of A by A n minus 1 is equals to A by n minus 1. Thank you.